Okay guys, now I'm going to talk about the single plane balance for the Vortex system. So as you can see, I have the infrared sensor mounted as close as possible to the nose cone of the impeller. I have the accelerometer mounted on top, and the cabling secured by blue tack or some other tacky substance like a clay, whatever you might want to use, and connected to the Vortex system. If I just pan over to the right, you can see the driver for the speed controller, the Vortex analyzer box, and also I have my laptop set up next to the mounting system, and I have my oscilloscope software as well as the analyzing tool for the balance. The analyzer software is quite simple to use. Quite simply, you start from the top and work your way down, entering the prompts as you go. Now, just to show you the sensitivity of the Vortex system, I'm going to turn on my the power to my speed controller, and the speed controller will cause the motor to beep, and the sensor is actually sensitive enough to pick up the oscillations of the beeping noise. So here it goes. So the first thing to do is to select your target frequency, or the frequency you're going to test throughout the balance. In my case, I've selected 40 Hertz. It seems to lie well on my suspension system, away from the natural frequency of the system. And so I'll switch over to the oscilloscope mode and pan over to the left. And I will spool up the inductor fan unit up to 40 Hertz and measure the initial vibration. Okay, so I just froze the frame of the imbalance, and as you can see on the screen, I have two waveforms. I have the red waveform, which is essentially the reference pulse coming from the white marker on the hub. The green sine wave is actually the imbalance measured by the accelerometer. So what you want to do for the initial imbalance is work out what the peak-to-peak voltage difference is. So on this software, if I look up the top, it gives me my voltage peak-to-peak for the green wave, sine wave, to be about 14 millivolts. So I'll put that as the first entry in the analysis tool. The next thing to do is to enter in the phase of the initial imbalance. The way to do this in this particular software is you can use a tool on the bottom which measures the time difference between any 2 points along the sine wave or the reference pulse. So the time difference between this pulse here and the second one is 24.9, or roughly 25 milliseconds. The time difference between this pulse and the peak of the sine wave is about 16.3 milliseconds. So what I can do now is I can enter these two values on the bottom of the analysis tool, and what the tool will do is actually calculate the phase shift between the two waves. Once you calculated the phase shift, you can enter that value underneath the vibration level or the original vibration. The next section of the balance run is to determine the trial unbalance weight. The trial weight is actually used by the Vortex system to determine what the final correction weight is. So what you do is you place a predetermined weight, a weight that you can select. It really doesn't matter what it is, probably nothing greater than the gram for this type of run, and you place it at the reference marker on the hub of the ducted fan unit. So I have a set of scales which has an accuracy of 0.001 grams, mainly used by jewelers. You can purchase this on eBay for about $20 or less. So I'll place a piece of blue tack on the balance. So it registers about 0.21 grams. So that'll be my trial weight I'll place on the hub of the ducted fan unit. So I have my trial weight attached to the hub of the ducted fan unit, and it's in line with the white marker. That white marker is the 0 degree reference position. So now I'll spool up to my reference or my target frequency, which is 40 Hertz in this case, and measure the vibration level as well as the phase shift between the reference pulse and the sine wave. So here we go. So now I've determined my vibration level, which is the voltage peak to peak. In this case it was about 17.5 millivolts, and I calculated my phase shift by determining the time difference between this peak and the next for the reference pulse, and the difference in time between the reference pulse and the first peak on the sine wave. I entered that data in the analysis tool in this section here. Once I've entered that data, it actually determines the correct balance weight required, as well as the location relative to the white marker or the 0 degree reference position. This is also shown on the graph on the right. Now with the graph on the right, you'll see a black star which actually refers to the 0 degree reference position. So my positive phase angle, which is indicated on the right, is going clockwise. So my balance solution says I need to apply 0.2 grams in a negative direction of about 70 degrees, and that's actually indicated by the green marker. So the red marker indicates where the trial weight was applied. The green marker indicates where the correct weight should be applied for the correct balance. So I've applied the correction weight 70 degrees counterclockwise from the 0 reference marker. This actually lies just behind this blade on the ducted fan unit. Now it's a good idea to apply the correction weight at the center plane of the fan. You don't want to apply it too far forward on the hub, too far back. That can actually induce a uncoupled balance, and it would actually make it a lot harder for you to achieve a final balance. Now what I'll do is, just to check the final vibration level, I'll spool up the ducted fan unit to our target frequency of 40 Hertz, and we can look at the final vibration level and see if there's an improvement. So this is a screenshot of the final vibration run. The final vibration level measured was about 4 millivolts peak to peak. That's just over 3 times lower than our original imbalance of 13.95 or 14 millivolts. Now you could run through this process again and actually fine tune the imbalance until you get an even lower residual imbalance. It's totally up to you on how far you want to go, but generally a first pass is typically good enough for running a ducted fan unit.